A lot of Americans are still skeptical about global climate change. And it's really good to be skeptical about things. Science itself is never certain about anything. You always have some kind of idea, and if that idea is proven wrong, then you abandon it and move on. We all better from it. So, in general, even though scientists are in general agreement, I think it's still good to say, is this really true? Is this really happening? But I think if you're going to stand toe to toe with them, you should also be speaking their language and on the terms of the general scientific community. So there are really three things that you'd have to look at to really make your own decision on global warming itself, or global climate change more specifically. The first is, how much carbon are we generating? Second is, how does that carbon affect the atmosphere? And the third is, how do these changes to atmospheric carbon dioxide affect global climate? So I'm going to try to get to those and see where we go from there. In order to get a really good grasp of the problem, first we need to understand how much carbon dioxide is being generated by transportation. I'll only consider transportation for the time being. In the world right now, we have about 1 billion cars, or 10 to the 9th power. Now this is an estimate for the whole world, but in the United States in particular, we actually have more cars than registered drivers. I'm taking as my estimate that each car drives 12,000 miles per year and gets about 30 miles at a gallon. Again, in some parts of the world, cars are getting much better than 30 miles at a gallon or driving less than 12,000 miles per year. But again, trying to take the aggregate of the whole world, in the United States, some cars drive far longer than 12,000 miles a year and get much less than 30 miles at a gallon. So I'm trying to aim for an estimate here. So let's try to figure out how many gallons per year this one example car is burning. So I take 1 gallon over 30 miles times 12,000 miles per year, and I get about 400 gallons per year that this one example car is burning. In a lot of engineering problems, you assume that gasoline behaves like pure octane. Gasoline itself is made up of many hydrocarbons, but octane is a pretty reasonable estimate of how it behaves on a thermodynamic level. So let's try to figure out how much carbon dioxide a gallon of octane fuel is burning. So C18H18 is octane, plus some amount of oxygen yields some amount of carbon dioxide and some amount of water. Well, let's only consider the carbon, because oxygen, we really don't care about how much oxygen we're burning or how much water we're producing, at least for the time being. So 1 mole of octane gives us 8 moles of carbon dioxide, balancing just the carbons. So let's figure out now in mass. So for the octane, that's 114 kilograms per kilomole by taking 8 carbons and 18 hydrogens. And likewise for carbon dioxide, I get 44 kilograms per kilomole by taking 1 carbon and 2 oxygens. So now 114 kilograms of octane gives me 352 kilograms of carbon dioxide. Hey, wait a minute. How am I getting more carbon dioxide than I'm putting fuel in? Well, keep in mind, too, a lot of this mass, this O2 section of it, is coming from the atmosphere itself. So the mass balance still works out. Gasoline has a density of about 0.74 grams per cubic centimeter, or about 2.8 kilograms per gallon. So now my 1 gallon of octane, or gasoline in this estimate, gives me 2.8 times 352 over 114 kilograms of carbon dioxide, or about 8.65 kilograms of carbon dioxide in a gallon of gas. So now my one example car burns 400 gallons of gas per year times 8.65 kilograms of carbon dioxide in the 1 gallon of gas. So my one car is giving me 3,460 kilograms of carbon dioxide in a single year. So let's take all the cars on the road. 3.460 times 1 billion cars gives me 3.460 times 10 to the 12th kilograms of carbon dioxide per year for all of the cars on the road. If we're going to speak in terms of a percentage change of carbon dioxide in the atmosphere, we must first get an understanding of how much carbon dioxide there is in the atmosphere. So first, we'll get an understanding of how much air there is in the atmosphere, and then the percentage from measurements. Let's try to get a feel now of how we understand how much air is in the atmosphere, because this seems like it'd be something that'd be impossible to measure. Imagine a column of air extending upward from the surface. Now, the thickness of the atmosphere itself is only a few hundred miles, and most of it's near the bottom. So I'm going to assume that the force of gravity per amount of mass is constant along this whole vertical column. So we understand at the bottom this pressure is the force over area, or the force is the pressure times the area. Well, force is mass times gravity because it's due to gravity, so mass is force over gravity. Combining these, I get the mass as the pressure times the area over the gravity. Well, what's the area? The area is the whole surface area of the Earth, 4 pi r squared. Carrying that out then, the mass is 4 pi pressure r squared over gravity. We know pi. Pressure, standard atmosphere, is 101.325 kilopascals, where a pascal is a newton per square meter. Radius to the Earth is about 6,400 kilometers. Gravity is 9.8 meters per second squared, or the way I prefer it, 9.8 newtons per kilogram. It's actually 9.81 in most textbooks. It's 9.79 near the North Pole, and it's 9.81. I'm sorry, I have that backwards. 9.81 near the pole and 9.79 at the equator. I generally like to use 9.8 because the figure itself isn't that precise. Neither is my atmosphere for that matter. So the mass is about 5.285 times 10 to the 18th kilograms for air. Now I'm putting the cart before the horse a little bit, and I looked this up ahead of time. The figure itself is actually about 2.5% less than you would come up with due to the displacement of the mountainous terrain taking up some of that volume. I'll go ahead and work with the official value here, but know that the derivation comes very close to double check that assessment. Currently, it's 2012 right now. Currently, the atmospheric carbon dioxide concentration is about 390 parts per million volume. Now, I take the molar masses of carbon dioxide in the atmosphere, 44.0 something, and I get up with 592 times 10 to the minus 6 mass fraction, or parts per million of mass. So let's take this now and figure out how much carbon dioxide there is in the atmosphere. 5.148 times 10 to the 18th times my 592 parts per million mass, I get 3.05 times 10 to the 15th kilograms of carbon dioxide. So we figured out how much carbon dioxide there is in the atmosphere and how much carbon dioxide humans are contributing per year from transportation alone. If you take those and divide them, you'll find that it takes, at the current rate of production from transportation alone, 882 years to double the carbon dioxide concentration in the atmosphere. Now this sounds really promising, but remember, humans have been around for thousands of years, and that's a little troubling to me. First of all, transportation only accounts for about a quarter of carbon dioxide emissions from humanity. Remember, it takes a lot of carbon dioxide emissions to generate these fossil fuels. And a lot of these fossil fuels don't end up in fuel tanks. They end up in power plants, coal-fired and oil-fired power plants. That's quite a bit of stuff we're putting in the atmosphere. This transportation-related carbon dioxide is not constant. Some estimates say that even within my own lifetime, we're going to be sitting at 2 billion cars. And so this 882-year figure is only going to be 440, and so on and so forth. Right now, in the year 2012, the atmospheric carbon dioxide concentration is about 390 parts per million volume. In 2000, it was 370, up 20 points. I would suggest Googling the Keeling experiment for more information on that. So for the last 12 years, we went up 5.4% for a full doubling over a period of 222 years. Now remember, I said that atmospheric carbon dioxide from humans, only a quarter of that comes from transportation, and the rest comes from other sources. So if the transportation numbers predicted 880 years to double, and the experimental evidence shows it would take 220 years to double, and other sources say that transportation is only a quarter, I would say this is very good evidence that yes, humans are causing the atmospheric carbon dioxide to increase. And I would say that any skeptic or anyone who wants to debunk this as a myth now has the burden of proof to furnish similar evidence, hard science evidence, to disprove this at this point. Thank you for your time.